Okay, here we go. We are Calc 1, Day 7, Lesson 15, Chapter 1, Section 3. Today we're going to talk about maximum and minimum values and optimization. We optimize when we want to find what's best. So optimization means finding the optimal or best situation or way to do something. Okay, so we can do this by finding actually the maximum or minimum. So maximum and minimum might be the highest point, or maybe the best point, or the lowest point, or maybe the cheapest point, or something like that. And those will give me my critical points that will answer these questions. Now, there's a couple things we have to look at, like what is maximum, what is minimum? Well, there's two kinds. So there's an absolute max. Absolute maximum is throughout the entire domain. So the highest point for the entire domain. So let's say I have something that looks like this, and I ask where the max is. I'm going to start at the beginning, I'm going to go clear to the end, I'm going to find out where my maximum point is, and that's going to be my absolute max. Okay, absolute minimum, same thing. Absolute minimum is my lowest point in all the domain. My lowest point in all the domain. So everywhere where it's defined, okay? Everywhere the domain is defined. Okay, so that would be, for instance, if I applied that to something, if I wanted to find the highest point in the world, that would be an absolute maximum, or the lowest point below sea level in the world, that would be an absolute minimum. But let's say then I changed it and said, well, what's the highest point in Pennsylvania? Now we're talking about local max and local minimum. There might be somewhere that's higher than lower than here, but if I specify my domain, so in a specific area where the highest point is, or a specific area the lowest point. Okay, so let's take a look at the book for some graphs, some beautiful graphs and some examples. Okay, so here we have talking about our maximum and minimum. Over here we have this, I'm going to move it up here a little bit for you to see. We have a graph here. This is my lowest point in the entire thing. So it would be my absolute minimum. And this would be my highest point in the entire thing. So it would be my absolute maximum. Sometimes people will say global maximum or global minimum instead of absolute. I actually like global a little bit better. That kind of gives the idea of everywhere. Okay, and if we look at the the local max and local minimums, the one thing that we have to remember is for local max and local minimums, we do not use the endpoints. Okay, because local max and local minimum, you have to be able to approach them from both sides. So similar to when we looked at limits, when you're going from the left and from the right, the local max and local minimum would have to have a left and a right. So down here, if you look at this picture, here we have this curve. And here, if I looked at this area, this would be my local minimum. If I looked at this area, this would be my local maximum. If I looked at this area, this would be my local minimum. But this one is also my absolute or global minimum of the graph, my lowest point. Some other examples, let's take the sine or cosine functions. You know they're periodic. They have a pattern. They go up, down, up, down, up, down, and it has a range of -1 to 1 for its vertical values, okay? And those will repeat after each period, so you could actually say, well, this would happen, cosine 2n plus 1 times pi would be -1, will be my minimum value, where n is any integer. So we can find a pattern or an expression that will give us that value of local minimum or local maximum. Now example 2 has part of a parabola, and here we have at 0, we have the 0 point being an absolute and local minimum. However, there is no high point in this parabola because it continues on forever. Okay, if there were dots here, that would mean there were endpoints. So this one doesn't have any dots, so that means it continues on forever. So there is no local maximum. So there doesn't have to be a local max, doesn't have to be a local min, and that takes us to example 3. Example 3 is an example here where you come up, you come straight, and then you go back up. Now interesting here, we don't have any local maxes or any local minimum. It's on a steady rise going from left to right. Right here it kind of flattens out, but it's still on a steady rise. So it has neither a maximum nor a minimum value. Let's look at example 4. Example 4, this is an interesting example. We have this graph here. We do have endpoints here, so we know that at the endpoints, these are not local maxes, okay? But it might be a global max. So let's see, what is my highest point here is at 1,5. I have, looks like I have a local maximum here, just a little hilly area. And I have a local minimum here. And this minimum is also my global minimum. So this is going to be my absolute minimum as well. However, I don't have an absolute maximum because these are endpoints. And these points are higher than this local max. So you can't say that this is the global max because you have points that are bigger than that. But they end at endpoints, so that is not a global max. So this one does not have a global max. All right, now we're going to take a look at the extreme value theorem. If we have a continuous interval, no breaks in the interval. Here's interval notation, including A through and including B. Then you're going to have an absolute maximum value and an absolute minimum value some number between the two of them. So this is saying if it is continuous on a closed interval and f attains an absolute maximum value and an absolute minimum value at some numbers in between. So here we have this, and here we have this, and then somewhere in between we have a local max and we have a local min. And we may have a global max and a global min as well. Now there are some problems with this theorem that we'll look at soon, but let's take a look at this one before we do. Here are my local max, or not my local, yeah, well it is a local max. Local max can be here, but this can also be my absolute max of the entire thing. And here is my absolute minimum. But again, this cannot be a local minimum because it's at an endpoint. Here I have a couple areas where I have a maximum point here and a maximum point here. However, it looks like they're about the same. So in that case, I would say that these would be local maxes, and this would be a local minimum. This one would also, though, be my global minimum because it's my lowest point of the entire thing. Now there are some problems with the extreme value theorem. So not all theorems are, they might have a proof, but that doesn't mean that they're flawless. So this is one that is the case. So here I have, if I look at the extreme values, I don't have a max here because this is an open circle. Can you see that? I'm on page 200. An open circle, which means it gets closer and closer and closer and closer and closer and closer. And every time I give you a number, you can give me a number bigger. So this is not a absolute max or a global max. And when I look at my minimum, this does have a minimum value at 2, 0 because it is a solid circle. Now this one's interesting because this one doesn't have a local max because it continues to get higher and higher and higher along this asymptote, but it also does not have a global minimum or an absolute minimum because I have an open circle, and just like over here, it continues to get closer and closer to it, but we can always get a little bit closer to it. So that takes us to 4. 4 is very important. It helps us solve a lot of different things. If f has a local maximum or a local minimum, then that means that its slope is 0. Okay, so here we go. We have this curve. And here's our tangent line. Our tangent line is on our critical point that changes from increasing to decreasing. This is a slope of 0. These are my critical points. Okay, and this will help me find my optimum value or my best way of doing things. All right, let's look at example 5. Example 5 says, here I have x to the x cubed, and as I come up, I flatten out and I come up this way. Now, I could actually draw a tangent line here through this process from where it rises and then it goes from concave down to concave up. So I actually have a horizontal tangent here, okay? However, we know that this does not mean that it's a local max or local minimum. So sometimes we might have this problem where we have this horizontal tangent on the curve. We have to check our graph to make sure. So again, making sure that you apply what you find out is very important. Now the absolute value graph here will have a local and an absolute minimum. A local and an absolute minimum. However, we do not say that it is differentiable at that point. Remember from few sections back, we said whenever we have this sharp curve, it's not differentiable. So there's a problem here if we say it has to have the f prime equal to 0 because f prime is not solvable at this point. However, there is a minimum here at 0. So, definition, critical number of a function of f is a number c in the domain of f such that either you can set the derivative equal to 0 or it doesn't exist. So this would also be considered a critical number because this is that example where it just simply doesn't exist. Okay, f of x equals x to the 3/5 times 4 minus x. All right, now if I differentiate this, I'm going to have a product rule. Now there's two ways I could do this. The first thing that I noticed when I looked at this is that there is no exponent out here. And I'm thinking to myself, it might as well be easier if I multiply it through and then differentiate it instead of applying the product rule. Do you see that? Now, if there was like a 3 or a 5 or some other number here, then I would apply the product rule. But to me, it really makes no sense to do that. I'm going to multiply this through, and this is 5 over 5, so remember this is x to the 8/5. Now, I'm going to go ahead and take my derivative. So I have 4 times 3/5, which is 12/5, x to the, if I subtract 1 from here, remember I'm subtracting 5 out of 5, so I'm going to get negative 2/5 minus 8/5 times x, subtract 5 out of 5 here, and I have 3/5. So now I need to clean this up a bit. Oh, luckily I have a common denominator here, so that's nice. Anyway, let's say we have 12 over 5, and then on the bottom of this fraction, we have the 5th root of x squared. Then on the over here, I have minus 8 x to the 3/5. Now I got to think about this. X to the 3/5. How would I make the common denominator? I would multiply the top and bottom of this one by x to the 2/5. When I do that, 3/5 plus 2/5 will be 1. So on the top, I just get 12 minus 8x, and then on the bottom, I have my 5 times the 5th root of x squared. Now, I have to find my critical numbers. So my critical numbers, again, according to my definition, would be where my first derivative is 0 or where it's not defined. So immediately I see that it doesn't exist at 0 because I can't put 0 in my denominator. So I will say f prime of x does not exist at 0. Okay. I can look at the top and say if I take the top, if it's equal to 0, then I will get the value of 0. So I solve for that. Negative 8x equals negative 12. Divide both sides by negative 8 and x equals 3/2. The next thing we're going to look at quickly is the closed interval method. And this is basically just some common sense. It's saying that, let's say you have a closed interval, numbers between a and b. Okay? You have numbers between a and b. find the values of f at the critical numbers of this function a from a to b. So you're looking for values from a to b for critical numbers. Find the values of the endpoints at the intervals. So the endpoints would be where a is and where b is. So you're going to find the areas in between that have critical numbers, and then you're going to find the endpoints. The largest values are going to be the absolute minimums or absolute maximums or the absolute maximums and absolute minimums of the graph. And that's it. Next, let's take a look at quickly example 8. Might as well just stay right here in the book. It's not very long example. I'm getting a glare from the light today. I hope you guys can see. And I'll try to tilt my book like this. I think that's a little better. All right, so here I have f of x, and here I have my interval. I'm looking at it being continuous. I know it's continuous because it's a polynomial. So polynomial is defined at all real numbers. It's continuous from -1/2 to 4. And if I use the closed interval method, that means I'm going to plug in my values at the end. So I'm going to plug in my -1/2 and plug in my 4. And then I'm also going to take my first derivative and I'm going to solve it for 0, and I will get 0 and 2. Once I plug those into the function, then I want to examine this and say, which one is the smallest? Which one is the largest? Well, I see that f of 2 of -3 is going to be my absolute minimum because it is my smallest number. But then I see that my f of 4 of my endpoint right here is my maximum value. So that's going to be my absolute max. So this is a method, basically we're saying how to find your absolute max and your absolute minimum. You find the derivative. Once you find the derivative, you set it equal to 0. Those are your critical numbers. But then if you have a closed interval, which means it has a beginning and the end, you have to check the endpoints as well, because the absolute max and the absolute minimum include your endpoints. We have one more example, kind of a fast lesson today. Example 10, we have the Hubble Space Telescope. I remember when this was deployed, 1990. I graduated from my bachelor's then, a long time ago. All right, here is my velocity function. Okay, my velocity function is here. I want to take a derivative because it's asking me for the acceleration of the shuttle between liftoff and jettison of the boosters. So my acceleration is the derivative of velocity. And remember, velocity is the derivative of the position function. Okay, but right now, if you're given velocity, you just need to go one more derivative to find your acceleration. So when we do that, this is the actual equation that we get for that. All right, what do I do with that? Well, I'm going to take a look at the closed interval method to say from beginning to end, I'm starting at 0. I'm starting at 0. I'm going to 126. So I want to examine those points. So here's 0, and here's my 126. And then I also want to solve this for 0. And when I get that value, I'm going to plug it in for t and compare all three. So my maximum acceleration is 62.87 feet per second, and the minimum acceleration is about 21.52 feet per second. Okay, so one is your endpoint and the other is your critical point. Okay, well, believe it or not, that is all for section 3.1. That's a nice short sections. Hey guys, how's it going? Okay, I didn't put my title on here, but we're still in Calc 1, And we are in day 5, 6, 7 still. But now we are in, I can't even remember what lesson, honestly. So 3, 2, we're just going to go over lightly. It's a lot of what you already know. And then we'll move on to 3, 3. Rolle's theorem. Similar to what we were talking about before. If you have a function and it satisfies the following 3 hypotheses. First, it's a continuous. You have to know, whoops, sorry, again, got to pull it down. Okay, let's do that again. Okay, so now you have a function and it is continuous on this closed interval. Now, it's continuous, so it is differentiable on the interval bigger than a and smaller than b. Now, if these two are the same, then there is some number c in between here where you have a slope of 0. For instance, let's say you have these graphs. Here I have a point, here I have a point. These 2 points are exactly the same height. There is a place in between those 2 points where I'm going to go from increasing to decreasing and have the slope of 0. Same here. These 2 points are in the exact same place and height, as far as height, not as far as the x value, but as far as the height, the y value. Okay, look, there are actually 2 places here where I'm going to have the slope of 0 because I have 2 critical points. And here's another example as well. Now, if we had a straight line over here, this whole thing would have the slope of 0 because a horizontal line has a slope of 0. So it also fits the theorem also. Okay, so the mean value theorem says that if it is continuous and if it is differentiable on that function, then there is a number c in between a and b such that the first derivative of c will be, really, you should recognize this. We've looked at it a couple times, right? This looks just like the slope formula. So here we go again. And f of b minus f of a all over b minus a. Notice if I take b minus a and I multiply it by both sides, b minus a on both sides, it'll reduce from the bottom here. And look at this. What is this? Point slope formula. Recognize it? Okay, so we're just back in algebra here, reviewing our slope function and our point slope formula as the mean value theorem. This here, let's look at example 5 real quick. Suppose we have f of 0 equals -3. Then we have a slope that is less than 5 for all the values of x. How large could f of 2 possibly be? Okay, so we know that we have f of 0 is -3. We're going to put those values into our function, and then we want to figure out how big our f of 2 could possibly be. So my f of 2 would be -3 plus 2 times my slope would be less than or equal to -3 plus 10, which would equal 7. So the largest possible point that it could possibly be with that slope is 7. In section 3.3, how derivatives affect the shape of a graph. All right, increasing and decreasing tests. When you take a derivative and the value of the slope is positive or bigger than 0 on an interval, then it is increasing on the interval. What that means is if I have an interval from here to here and I have a positive value for slope, that means I'm going up. Makes sense? Because if slope is positive, then I do go up, right? But if I go down, my slope is negative, let's say from here to here, then I come down. All right? Not new concepts again, but we can use these concepts with slope to figure out how to graph a function. Okay, so let's take a look at example 1 and let's do some math. F of x equals 3x to the 4th minus 4x cubed minus 12x squared plus 5. Okay, this says find where it's increasing and find where it's decreasing. So the first thing that we're going to do, oh, I know you can't see. And now I need to take the first derivative. And when I do that, I'll have 12x cubed minus 12x squared minus 24x. And the other is gone. So I can factor out a 12x. And when I do that, I have x squared minus x minus 2. Okay, let's see, can I factor that? Looks like I have my x values to 1. I have a negative here. So I'm going to have my factoring point to be this. Now, I need to know where is it 0, because those would be my critical points where it changes from increasing to decreasing. So I need to know those values. So it looks like that will happen at 0. It looks like that will happen at 2. And it looks like that will happen at -1. So how do I know if it's increasing or decreasing? Well, there's a simple method that you can do. You can just make a number line. -1, we'll put 0 here, 1 here, and 2 here. Okay? All right, so here are my areas where I have the slope of 0. I want to know if it's increasing or decreasing in those areas. Well, first, I have to pick a number that is smaller than -1. And when I pick a number that's smaller than -1, then, and the easiest way to do is just to keep this factored like this, 12x, x minus 2, x plus 1. And that's the table that they have for you there on page 214. And if I first look at a number in this area, let's say -2, just try any number, you pick it. Okay, all I need to know is this negative or is this positive? I don't even need to know the value, okay? So if I put a -2 in here, this value is going to be negative. If I put a -2 in here, this value is going to be negative. If I put a -2 in here, this value is going to be negative. And a negative times a negative times a negative will give me the product of negative, which means it will be decreasing from -infinity until I reach -1. Until I reach -1, right? Because at -1, the slope is 0, and that's where it changes, maybe, from increasing to decreasing. We'll find out that sometimes it doesn't necessarily change. Sometimes it just does something else, which we'll look closely at. All right, so now that was where my x value is less than -1. Now I'm going to look at if it's bigger than -1, but it's smaller than my next point in question, which is 0. So I'm going to find a number between -1 and 0, and I'm going to test it. So let's just pick -1/2. And again, we don't need to know the value, we just need to know the sign. So if I would put -1/2 in here, I will get negative. If I put -1/2 in here, I will get negative. If I put -1/2 in here, I will get positive. And I multiply all three of these together, I get positive. So now this shows that I'm increasing because I have a positive value between -1 and 0. My next point in question is between 0 and 2. So I have greater than 0, less than 2. Again, I just care about the signs. So I'm going to pick the number 1. This will be positive. Pick the number 1. This will be negative. Pick the number 1. This will be positive. Multiply these together and I get a negative, and it looks like I'm decreasing. Now, it's not always going to alternate, so do not fall into that trap, as you will see. And then finally, my last spot is going to be if it's bigger than 2. So if it's bigger than 2, let's try the number 3. And again, I do the same thing. Throw 3 in here, I get positive. 3 in here, I get positive. 3 in here, I get positive. Positive times positive times positive is positive. And it is, in fact, increasing after 2. Now, let's take a look at the graph. Here we go. As it said before, I'm decreasing from negative infinity to negative 1. Then I'm increasing from negative 1 to 0. Then I'm decreasing from 0 to 2. And then I'm increasing from there to infinity. Okay? Now, I didn't put my numbers in to figure out what those critical points were, but it's not that hard to do that. All I would have to do is to put my values in to my original equation to find out what my point would be. First derivative test says, suppose that C is a critical number of a continuous function. F prime changes from positive to negative, then it has a local maximum. If F prime changes from negative to positive, then it has a local minimum. If F prime does not change the sign, it does not have a local max nor a local minimum. And this is where we're going to talk about figure 3. So figure 3 shows you as I'm increasing and then decreasing, this would be my local max. Here I'm decreasing and then I'm increasing, this will be my local min. Here though, I'm increasing and then I have my slope of 0 right here, but I'm continuing to increase. So I go positive, 0, positive. So in this case, I don't have a local max or a local min. Also here, I'm decreasing. Same thing. I get to this point. I have a horizontal tangent. No maximum or minimum. Okay? The next example says find the local maximum and minimum values of example 1. So simply all you have to do, like I said before, is to plug those values that you tested where you got 0 into the original function, because that will give you your points. So let's go back and review. We had negative 1, 0, and 2. We had negative 1, 0, and 2. So if I plug in negative 1 into my original function, let me put it back over here. 3x to the 4th minus 4x cubed minus 12x squared plus 5. I plug this in, negative 1, I will get 0. That would be a local minimum point. If I plug f of 2 in, I get negative 27, also a local minimum point. F of 0 is a local maximum point because it changes from positive to negative. So that's how you get your values. Okay, let's do another one. Okay, now we're going to look at what f double prime says about f. F double prime describes whether something will be concave up or concave down. Concave up means I'm going to have a slope smaller, steeper, and steepier. Okay? Or concave down. Now, how I usually tell people to remember it is, you can visualize this as a cup. If I were to fill this up, that would be my concave up. My concave down would be everything spilling out, concave down. After you find the first derivative, you find the second derivative to find out whether it's concave up or concave down. So we're going to take a look at that. Okay, so this is called the concavity test, the second derivative. So we're going to look at whether it's bigger than 0 after I take the second derivative and set it equal to 0, or less than 0. Okay, if it's greater than 0, then it's going to be concave up. If it's less than 0, then it's going to be concave down. Here again is an example: concave up, concave down. All right, this point where it goes from concave up to concave down has a name. Just like our critical points had a name when it goes from increasing to decreasing, when it goes from concave up to concave down, it is called an inflection point. Okay, so let's examine this graph over here. You can see that this is all concave up until I get to here. Then it seems to switch from concave up to concave down for the rest of the way. So this point where it changes from concave up then to concave down is called my inflection point. Now, if you have your second derivative and it's continuous near where you're evaluating it at C, your first derivative, if you set it equal to 0 and your second derivative is greater than 0, then f has a local minimum at C. If your first derivative is equal to 0 and your second derivative is less than 0, then your function has a local maximum at C. All right, so let's take a look at a full problem. Let's discuss the curve of example 6. Y equals x to the 4th minus 4x cubed. Okay, now we're going to use what we know about derivatives, critical points, and inflection points, and we're going to use that to sketch a graph. First thing I'm going to do is find my first derivative. When I do that, I will have 4x cubed minus 12x squared. I'm going to set that equal to 0. 4x cubed minus 12x squared. Set it equal to 0. Factor out 4x squared, and I get x minus 3 here, and this is equal to 0. Okay, so my possible critical values, we call them, possible critical values would be 0 and 3. Okay, possible critical values, 0 and 3. All right, so let's test this. We want to find out if these values are critical points or if they're not. So here I have my graph again that we talked about before. I have my point 0, I have my point 3. I need to check before it, I need to check in the middle, and I need to check after it. So the first thing I want to do is check less than 0. And I check less than 0, I'm measuring it in my first derivative, so I want to know whether or not it's positive or it's negative. That's all I care about, the sign. I don't care about it, the value right now. So if I pick a number less than 0, let's say -1, and I put -1 in here, -1 squared is going to be +1, so this remains positive. And if I put -1 here, I will get negative. And a positive times a negative is a negative. So that means that I'm going to be decreasing. Now if I look between 0 and 3, let's say 1, I throw 1 in here, I'm going to have positive. I throw 1 in here, I'm going to have negative, and I see that I have negative, and there was no change. No change between the two. If there's no change between the two, that means that this is not a critical point. Not a critical point at 0. There's no change. Okay, now let's look at greater than 3. Again, just caring about the signs. If I put 4 in here, this will be positive. This is going to be positive. Now I have a change here from negative to positive, so my value 3 will be a critical point. So I have a critical point at 3. Now, I should probably figure out what those values are at these possible critical points. So if I'm going to go back to my original equation and plug in 0, then I will get 0. So I know there's a point right here. Then if I plug in my value of 3 to the 4th, I'm going to have 81 minus 4 times 3 to the 3rd, which is 27. 27 times 4 is 108. And then I'm going to subtract from 108, 81, and I get negative 27 as a value. So I have over here at 3, 1, 2, 3, way down here, I have negative 27. So I'll have to do these in 5, 10, 15, 20, 25. We'll do it that way. Okay? All right. So far, what have I done? I have taken the first derivative. I found where it could possibly be critical points. I tested them to see if they were critical points. There was no change here, so it's not a critical point. But I do want to go ahead and throw these into my original equation to see where these do fall on my graph. Now, so far, all I know is that I'm decreasing to decreasing, and then I'm increasing. So somehow I'm going decreasing, decreasing, and then increasing here. Okay? Let's take my second derivative to see if that can tell me anything. So I go back up to here. This was my first derivative. And I'm going to come down here and take my second derivative. So I have 12x squared minus 24x. And then I can factor out a 12x. And I have x minus 2. For my second derivative, this again was my y double prime. I'm going to set this equal to 0. And I have x equals 0 and x equals 2. Well, interesting that I got 0 for both of them. Maybe since it wasn't a critical point, maybe it's an inflection point. So let's check that out and see. So just like I tested the critical points, I do the same thing for the inflection points. This time though, I'm going to use my second derivative, which is 12x and x minus 2. Here my values are 0 and 2. So again, I'm going to look at a number line of sorts. I'm going to have 0 here, 2 here. I want a value here to check, a value here to check, and a value here to check. So let's go less than 0 first. I can put -1. If I put -1 value in here, I will have a negative. If I put a -1 value in here, I again will have a negative. And a negative multiplied together will give me a positive. And a positive means I'm going to be concave up. Between 0 and 2, I can choose the value 1. Why not? It's simple enough. So I can choose the value 1. This will be positive. This will be negative. This will be negative. And this is concave down. Now I know why my 0 was not a critical point. It wasn't a critical point because it's an inflection point. Okay? Now let's try to go bigger than 2. Choose the value 3. I get a positive, which is positive. Once again, concave up. Okay, so this gives me some idea about what's going on. Other than that, let's throw 2 into our original function to see if we can get another point here since it's right in this area. So we're going to throw 2 in here, and 2 to the 4th is 16. Minus 4 times 2 to the 3rd, which is 8. So 16 minus 32 is -16. So I do have a point on the graph that is at 2 and then -16. So I did these in 5s, 5, 10, 15, right here about -16. And that is my inflection point. Okay. All right. Now, the only other thing I need are, I call them my wings on each end. I need a point over here and a point over here, a guide point to kind of tell me how steep am I coming into this and how steep am I going out of it. So let's throw a couple more points in just to take a look. I'm going to have -1 here. If I put -1 into x to the 4th, I get +1 minus 4 times -1 cubed. This is going to become +4. So this value will give me 5. So I have -1, 5. Okay, now let's do a point over here. Might as well look at 4. 4 to the 4th, which is 16 squared. It's 256, I think. And then minus 4 to the 3rd. 4 times 4 is 16, 48. So I'm going to have 48 times 4. My guide point on the end here of 64. Okay, so I'm going to go way up here. All right, now let's take a look at what we know. Right now it still looks like a bunch of dots, but if I sketch, I'm coming down and I know that I'm concave up at first. So I'm coming down and I'm concave up. But then I hit this 0 point, and the 0 point I go from concave up. 0 point I go from concave up to concave down. So I turn back around this way. And then I hit another inflection point. So I go from concave down back to concave up. And then I'm going to shoot straight up, steep, to hit my other guide point way up there. We'll take a look at example 7. F of x equals x to the 2/3, 6 minus x, 1/3, and we're going to calculate the first two derivatives and possibly sketch the graph. All right, well, this is going to be an interesting one, I can tell you that right away. So the first two derivatives, if I do that, I'm going to, and again, this is where I have 1/3 out here, so I'm not going to be multiplying this in, unfortunately. So I would have to use the product rule, okay? And they went ahead and give us the first two derivatives there because we've already had a test on that, right? So we have f of x equals, the first derivative is 4 minus x over x to the 1/3, 6 minus x to the 2/3. Now, definitely would not hurt you to practice differentiating to make sure that you get that. Then do it again. Second derivative, we're going to have -8. And then on the bottom, x to the 4/3, 6 minus x to the 5/3. Okay? We're going to take a look at this graph, or this table. Here we have on the table, shows where my first derivative is 0. My first derivative is 0. I want to look at the top and say, where would this be 0? It would be 0 at x equals 4. So that tells me possible critical point at 4. F prime of x does not exist, though, when x equals 0, because I have 0 down here multiplied by a quantity. It would wipe this whole thing out and make it undefined. So x equals 0, and then f doesn't exist at x equals 0. Now the other critical point that I can take a look at is x equals 6, because if I put 6 in here, I will also get 0 in my denominator. So either 0 or 6 would give me an undefined. That means I'm going to check all these points before 0, from 0 to 4, from 4 to 6, and then bigger than 6. When I do that, I see I'm decreasing, then I'm increasing, then I'm decreasing, and then I continue to decrease. So upon first inspection, it looks like I might have a critical point right here and maybe right here, but not here. We're going to take a look at this graph. Like I said, this is an interesting one, okay? Here is why it isn't defined at 0. It comes down and it does this sharp turn, so it's not definable here. But it is decreasing and then increasing. So that's interesting. Decreasing to increasing, but again, not defined here. Then it travels up once I get to 4. Now I have a critical point where I'm going to go from increasing to decreasing. Okay? Now the second derivative, if I take a look at that, I'm going to look at it and say, well, now I need to examine the top and bottom. Again, I have a problem at the bottom. My problem at the bottom is it will be undefined at 0 and it will be undefined at 6. And what happens here when I test them is that it goes from concave down and switches to concave up at 6, because 6 is an inflection point. Okay, 6 is an inflection point. All right, well, I hope that this lesson helped you. Good thing it's a video. You can just go back and forth whenever you want. And I will talk to you guys on Wednesday and hope you're all doing well. So, peace.